start. Okay, so let's start. So we are doing DC circuit. Okay, it's very easy. So here you have all the physical quantities again. The time has to be in seconds. So if you are given minutes, you have to turn that into seconds. Energy in joule. Okay, Q is in coulomb. Okay, the amount of charge. The current is the amount of coulombs being produced by a power supply, for example, per second. Okay, so the unit is amps, but it means coulombs per second, or Q in coulombs and T over T, so per second for 1 second. And then this here, it should always have a delta because it means a drop, a change. Okay, so voltage, remember, could be a conceptual equation. The voltage is the potential energy for 1 coulomb per coulomb. So even if it's going into a DC circuit, if you have a 9-volt battery, it means 9 joule per coulomb. Okay, and then that 9 joule per coulomb, it's going to be delivered to the load and then it's coming back. So it should be really a delta, and you have to think of that as a drop, a voltage drop, like losing height. Power, again, it's energy per second, so that will be watt. Okay, so the amount of energy consumed by a load or produced by a power supply per second. Okay, and then you have Ohm's law. So you have to read that as the voltage drop across a load. So it's between point A and B. So it's a voltage drop across the load. Okay, it's going to be equals to the current going through the load times the resistance. Okay, so it means more current, more voltage means more pressure, so more current. So voltage is like pressure. And then what else? And then you have these equations, the power of a load or power supply is voltage times current. Okay, voltage drop times current. And if you have a ohmic load, like a resistor, then you can use Ohm's law. Okay, so it's a review, and I forgot where we stopped. Okay, I know. Here, so the resistance of a connecting wire is proportional to the length. So if you increase the length, okay, you're going to increase the resistance, inversely proportional to the area, because if you increase the cross section of a wire, that means you have less resistance. Okay, it works like blood flowing in blood arteries or blood what? Blood thing, blood pipe, like blood what? Help me. Blood are flowing in veins, okay, in veins, right? So the amount of blood flowing is inversely proportional. More cross section, more blood. If you increase the length, you're gonna have less blood, right, or more resistance, and it depends also on the material. Okay, so for example, here that here is a constant. It's called resistivity, and you see aluminium is better than copper, better than gold, and so forth and so on. Okay, so as you go this way, you're going to increase the resistance. As you go that way, you decrease the resistance. It makes sense. We are using copper because aluminium, is too much malleable, too much flexible for the wiring, and gold obviously is too expensive. So copper, that's what is used. And here it's a simple application. I'm just gonna, it's easy, right? So you can write down the equation quickly and see if you get the right answer. So if you're in electronics, in the US, the size of a wire is measured in gauge. And it's counterintuitive. Larger the gauge, thinner the wires. If you have a very large gouge here, it's going to be a thin wire. Small gouge means thick wire for some reason. Okay, so you can do that. 35 is the length. And then you have the cross section. And then it's copper. So you use that here. Copper is this. Okay, so you do 1.72 times 10 to the negative 8. You multiply by the length and you divide by the cross section. You can do that with your TI. Okay, it's easy. Okay, so they do the computation for you. You have the constant here for copper, the length of the wire, and then here you have the cross section. Okay, 1.2 ohms. And for this one, you should find 0.99 ohms. And talking about blood, it works exactly the same way. If you increase the blood pressure, okay, so it's like the voltage, you're going to increase the amount of blood per minute, but it depends on the resistance. And that resistance here for blood depends on the length of the blood vessels. Okay, that's the word I was looking, and inversely proportional to the area, and it depends on the viscosity of the blood. So you can totally make the connection. Good morning. Okay. So that's easy, okay? Everything is easy here. Okay. You have to be careful when well, you don't have to worry in Florida, but in New York, my students, it was cold in their dorms, so they will buy those cheap heater there, but it's never long enough. So they will get an extension cord at the dollar stores, but in that case, you have to be very careful, okay? You have to read the current, the maximum current it can take. Because if you get a thinner wire, so cross section is smaller, okay? So you're going to increase the resistance of that wire there, okay? And more energy will be lost to heat. So you can actually start a fire because it's like a load here. It's like you add a load. So if I here it's like okay, you have your power supply, which is AC, right? So you have 120 volt, and then that wire here is like having a very large resistance R. And then here you have the load, and maybe you have some resistance here, and then you have a very large resistance inside here too. So if this resistance is very large, that means the power consumed, okay, it's going to be Ri square. So if you have a very large resistance, you're going to have a lot of heat produced there, and you can start a fire. So be careful. They have a little tag, and you have to read the tag here, okay, how much current it can take. Otherwise, before it's going to start a fire. So, but in Florida, we don't have to worry about that, which is good. Okay, here is a very nice application for those going into medical field, for example. You can measure the amount of blood flowing to see if there is some resistance, right? If maybe you have clotting happening, maybe, I don't know, something is happening. So the way you do it is that you're gonna have a current source. So you know the current. So the current is gonna flow from here to there. You're going to measure the voltage, you have the length, so you can measure the resistance and you know if something is happening inside. Okay, so it's a very nice application and it's not invasive. Okay, now I'm not going to go too much in details, but the resistance of a wire also depends on the temperature. So if you increase the temperature, you're going to increase the resistance. Because if you increase the temperature, the molecule is going to shake faster. So it's going to make it harder for the electrons to get through. So it's an easy equation to apply. If you increase the temperature of a conductor, you're going to increase the resistance. Except except if it's a semiconductor. Semiconductor, they do the opposite. So if you increase the temperature, you decrease the resistance. So you use semiconductor as a thermometer. Okay, that's easy. Nothing easy. It's easy. It's a easy unit. Okay, electric power. This is always true. Okay, so voltage across times the current going through. Okay, so it's true for power supply or loads. Okay, but if you have a resistor or a load that behaves like a resistor, then you can use that equation because you can plug in Ohm's law. Okay, so this you can use only if you have like a resistor like load. Okay, easy. Okay, transmission here. So you see the power that you lose along that connecting wire, okay, equals the resistance. Okay, so the resistance, you cannot change the resistance that much. Okay, you can, if you decrease the resistance, that means you will have to make very thick cable, and that will cost a lot of money. So this you cannot touch too much, but you want to make sure to decrease the amount of energy lost between the power plant and the consumers, right? Because otherwise they will have to pay. It's not you that it's not for you to pay. So they want to make sure that they need to minimize the amount of energy lost through heat in those high tension lines. Okay, so of course you can decrease the resistance a little bit, but the best way is to decrease the current. But if you decrease the current, you have to increase the voltage. So what they will do at the power plant, they go from 10,000 volt, for example, they were going to boost it to 100,000 volt. So for the same power, if you multiply the voltage by 10, the current will be divided by 10. If you have less current, if the current is divided by 10, the current square is divided by 100. So you are losing less energy to heat. So that's why those lines are high tension. So you need some kind of transformer to boost, okay, to boost the voltage up. Is that clear? So you want very high voltage, and then you get to the city, you're gonna go down 5,000 volt and then down to 120 volt. Okay. So here it's super easy. You can. I just want to show you the schematic I'm gonna use. My methodology. You don't have to use my methodology, but just to show you how I do it, and why don't you do it? So this comes from the algebra based book, but I just want to show you how I do it, the engineering way. So you think of voltage as altitude. So you start with 3 volt, and then here you're gonna have a load. Okay, and then you go back to ground. That's how I do it. And the current here is like, this is like a pipe, and this is 0.4 amps. So it's a drop. You go from high up to the ground. This is the ground. So from 3 to 0, the voltage drop is 3 volt. Okay, so then you can use Ohm's law to find the resistance. Or you can use, so here they don't ask the resistance, they just want you to find the power. Okay, so power is the voltage drop across times the current through. Okay, remember this is across and this is through. I, yeah, that's exactly right. Right? It will be a joule per coulomb, and that's the coulomb should be joule per coulomb, and then you have coulomb per second, and you have joules per second, which is watt. You're right. Okay, so the voltage is 3 times 0.4. That's going to be 1.2 watt. Okay, so 1.2 watt delivered by the power supply and consumed by the load, and you just have one load. Okay, did you get that? And B time is 5.5 minutes, which is 60 seconds. Energy, the energy is the power times the time. So that's going to be 1.2 times 5.5 times 60. Okay? Which is 396 joules. Okay? It's very simple. Once you understand the concept, that's not that hard. Any question? Okay. So this is electrical circuit symbols. So that's a resistor, ammeter to measure the current, voltmeter across. Inductor, it's just a coil, solenoid. Transformer, that will be the ground. I'm going to use that. That's a diode, that's a capacitor, that's a lamp. Obviously, that's a switch. Okay, so circuit in series, it says, yes, circuit in series is when you have two loads next to each other. Okay, so it means it's going to be the same current flowing through them. Okay, so that's easy. Okay, so let's take an example here. What does it say? 48, skip to 49. Okay, I'm going to show you how to do it. So this is called circuit in series. Again, that's easy. I'm just going to show you the methodology. Because those going to electrical engineering, you will have to take a more advanced class in the circuit analysis. Okay, so the way you do it, you start with the power supply, which is 12 volt. So that's high up, right? On top of the mountain. And then you have a 6 ohm, and you follow. Pum, 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 pum. 6 ohm. You keep going. Pum, 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 pum. 3 ohm, right? So we're going to say that everything happens like, you see, you have a little zigzag and then you have another zigzag. So everything happens like you have a big zigzag, and the resistance here will be 9 ohm. So this is called the equivalent resistance. And when you have a circuit in series, so one resistance connected to another resistance connected to another resistance, you just add the resistances, and this is called the equivalent resistance. Okay, it's easy to understand. So once you are here, so this is just a mathematical trick to find, for example, the current, okay, drained from the battery. So you start with this step, then you go to that step. Once you are here, you're going to say, okay, I go from 12, boom, I drop here to the ground. So that voltage drop is 12 volt. Okay, so now if you want to find the current, you just use Ohm's law. Okay, it's easy, right? You have to think of voltage like a drop. You are dropping height. It's like a height that you are losing. You are losing height. So that means 12 equals 9 times the current. So the current is 12 divided by 9. amps. Okay, and then the power consumed by each load. So then you come back here. Okay, look what you are doing. So this is 1.3 repeating. Do you agree? So you go back one step. Okay, that will be the methodology. So now you see it's like water flowing downhill. That will be 1.3 repeating. So let's say just for you to see the methodology. So you see now I can measure the voltage drop across this load, and I can measure the voltage drop across this load. So it's like measuring height. So if you do 6 times 1.33333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333333 I should do it in my head, right? 8. Yes, so that will be 8 volt. And how much is left? So you can do 3 times 1.33333. What do you get? 4. Does it make sense? Yes. Look, 12 volt, boom, you drop by 8, and boom, you drop by 4, and you are back to 0, and then you get a boost again. So this is called Kirchhoff law for voltage. This is a circuit in series, and you see that the sum of all the voltages equals the voltage of the power supply. Okay, once you have 8, you know this one will be 4 because 8 plus 4 is 12. But you have to measure the height. Okay, it's like you start from 12 yards and you drop by 8, so 4 is left. Now, if I want to find the voltage, the power by 6 ohms, so it's consuming. So I can do 8 times 1.3 watt. Consumed by the 3 ohm, that will be 4 times 1.3 repeating, and then the power supply by the battery, it's going to be 12 times 1.3. Does it make sense? So it's conservation of energy. That power supply providing that amount of energy is going to be the power consumed by this one plus the power consumed by that one. So it's conservation of energy. Okay? So if you use that methodology, it's going to be easy. If you think of voltage like height. Okay, yes, you have the number, it adds up. So that will be the power supply, the power provided by the power supply. Okay, so lots of application. Okay, what do you think here? What do they want? In A, the second has the same rate B. Okay. Find the voltage across the top resistor. Okay. So one thing that students forget is that if there is no current flowing through a load, so if you have no current flowing through the load, the voltage equals 0. If you have no current flowing, the resistance equals 0. Okay, so what do you think? So here you have 6 volt, and you have a R, and you have a R. So you see R and R means they have the same appetite. It makes sense, right? So what do you think the voltage drop is going to be across each one of them? Huh? 3, right? You have 6 cookies and 2 kids, and you want to be fair. So each one get 3. So the voltage drop here is 3, the voltage drop is 3. Okay? Or you can do the long way, you can say 6 volt, everything happens like I have a big zigzag of 2R. Okay, the voltage drop is 6 volt. So 6 equals 2R times the current, and you can you can solve also this way. But here you see the voltage is the same because the appetite is the same. Yes. Okay, so anyway, so the voltage drop is, what do you think the voltage drop here is? Very good, it's 0 volt. And sometimes it can be confusing for students because they want to put a voltage, but no, the current cannot flow here because it's an open circuit. So if there is no voltage, now if there is no current flowing through, there is no voltage drop. So that's going to be 0. And this one will be 6. It doesn't, yeah, so C has a larger voltage than A and then B. Okay? Um, so you have something, you can look into it, but I just show you the trick. This is called a voltage divider. It happens like when you have a power supply. Let's say you play with Arduino, which is a microcontroller. Arduino is going to provide 5 volts. And then when you get some sensors, the sensors don't want 5 volts. Some of them want 3.3 volts. So you have to decrease the voltage. So in that case, we use what is called a voltage divider. So I will let you do the math. Okay, you're using Ohm's law, you see, you have all the details, so you can do that on your own. But basically, I give you the trick, like a shortcut. So it's called a voltage divider. Okay, you need to have 2 resistance. Okay, so in that case, it goes like this. You have here your input. That will be your input. So for example, 5 volt. Let's say you have 5 volt for Arduino. And then you have a resistance R1. And then you have a resistance R2. Okay, that voltage here, that's what we call the output. Okay, but because if you have Arduino, for example, so that will be your source, and here that will be your sensor. And you want the sensor to have something less than 5 volt. Okay, so the voltage drop here, let's say it's V out, and this is V in. Agree? And it's very simple. Using Ohm's law, you can show that V out is to V in what R2 is to R1 plus R2. So this is called voltage divider. And you can show that with Ohm's law. It's easy to remember. V out is to V in what R2 is to R1 plus R2. So that way you can get the voltage output that you want. Okay? So let's take an example. Okay, so that's from Arduino stuff. And find V out. Okay, so that will be your output. So that will be your sensor. And find V out. Don't stare, do. Okay, so it's a voltage divider. This is V out. This is V in. So I'm going to say V out is to V in what? You see, this goes with V out. So what? R2 is to R1 plus R2. Okay, so V out is to 5. R2 is to R1 plus R2. So there is a K. Usually you always use kilo ohms. But you see, you have kilo here and you have kilo there, so we don't worry about that. So it's going to be 20 over 30. Bye-bye. So V out is 2/3 of 5, which is, yeah, 3.3 volts. And if you play with Arduino or microcontroller, many little sensors, they don't want 5 volt, they want 3.3 volt. So you are using a voltage divider. So this is 3.3 volt. That's going to be 1.7 volts, something like this. So the larger the resistance, larger drop. Okay. Okay, that's cool. Okay, so then he explained that in that slide explained that if you have a battery, remember a battery, it's like a box that you cannot open. Inside, you have an internal resistance that will still that will take away some voltage. Okay, so if you want to know how much is left for the load, so if you have we did that last time. If you have an internal resistance, okay, so it's like you have your battery here, and then you have a sneaky little resistance here hiding inside, and then you have your load. Okay, so the load, that's what you want. Okay, so that will be V out. So that will be the terminal voltage. That will be your headlight, and that will be inside the battery, the 12 volt. So let's say it's a car battery. Let's say this is 12 volt. So we can do the same thing. V out, that is left for your, I don't know, starting the car will be is to 12 volt, what R is to R. Okay, so you can apply the same equation. We did that last time. So if you have a new battery, this one you can forget. But if the battery gets old, then you have to worry about that. Okay. Okay, try to do that. It's a little bit tricky. So if a current does not go through a resistance, there is no voltage. If there is no current, sorry, but there is no voltage drop. If there is no current, there is no voltage drop. So if there is no current going through a resistance, you can replace the resistance just by a wire. So help each other. What do you think? So you have the current going this way, and there is no path here. So the current cannot go this way. It's going to go back this way, that way. So here, there is no current here. There is no current. So everything happens like you just have a connecting wire. It's like it's not there. There is no voltage drop. So the voltmeter, it's okay. You're going to put your voltmeter here. So the voltage drop between A and B will be equals to the voltage drop here. Because we say the connecting wire has no resistance, so there is no voltage drop. So it's just a wire here. Right? So what do you think the voltage drop will be between A and B? Huh? B, very good. Right? So because now you have two kids, and so same appetite, So each one of them get half of the cookies. So each time there is no current, if you have a resistance and the current equals 0, and so the voltage drop equals 0, there is no current flowing. So it's just a connecting wire. Okay? It's a little bit tricky. Okay, Wheatstone bridge. So usually to measure resistance when you are in a lab, you're going to use a ohm meter, multimeter. But if you want something very precise, you're going to use what is called a Wheatstone bridge. And you do that in the lab. So the goal of this setup here is to measure an unknown resistance here, R3, with a lot of precision. Okay, so that's the goal, is to find the resistance R3. And you have a setup here. And then between those 2 points, you have a galvanometer. So it's like something to measure the current. Okay, and you want to make sure, is it the unknown? What is the unknown? Unknown, oh no, the unknown is R4. Okay, I rewind. I'm coming back. So this setup is to measure R4. Okay, between those 2 points, you have a galvanometer, so it's to measure the current. And here you have a variable resistor. So you're going to change R3. Okay, it's like a knob. You're going to change R3 until there is no current. I'm losing my voice. Flowing in there. Are you with me? So if there is no current flowing, for current to flow, you need a voltage drop. So it means there is no voltage drop, like it's water flowing. If you want water to flow, you need some kind of change in altitude, right? Otherwise, the water will not move. So no current flow. So that means the voltage will be the Okay, here there is no current flowing. Do you agree? So it's like two conductors connected to each other, so they will have the same voltage. Okay, the voltage will be the same. This voltage here will be exactly the same voltage there. And this is the ground. So it's like you start from uphill, okay? I'm following this way. I have a resistance R1, I have a resistance R3, and I go to the ground. And this branch here, I start with E. I have a resistance R2, okay, connecting here, and then I have a resistance R4. But that voltage here is the same as this one because they are connected with a conductor. Okay, remember, if you have a Van Graaff generator, you connect that to someone, that someone will be isolated. So if this is 5,000 volt, this one will be 5,000 volt. So the voltage here is the same. Okay, so now try to apply the voltage divider. So you have two voltage divider. And this voltage here is the same as that one. Okay, so I don't know, I'm going to call that V out. And this is V out. So apply the equation for the voltage divider. Okay, so V out is to E what R3 is to R1 plus R3. Okay, and the goal is to find R4. So do it. Just apply the voltage divider to this one and the voltage divider to that one. Okay, so I have, what do I have? V out is to the input. So V out is to input, what R3 is to R1 plus R3. And I have the same thing for this one. V out is to the input, what R4 is to R2 plus R4. Okay, so once you have that, you flip. Flip this one, flip that one. Because we want to isolate R4. So gonna flip this one. So R1 plus R3 over R3 equals R2 plus R4 over R4. Agree? Distribute the denominator. So it's going to be R1 over R3 plus 1. Okay, you divide here, you divide there. Equals R2 over R4 plus 1. Are you with me? So this is just algebra. You flip distribution. It's a distribution for division. It goes bye-bye. Okay, you go bye-bye. So you have R1 over R3 equals R2 over R4. And that's it. You can isolate R4. So that's the Winston Bridge equation. So again, you have the goal is to find that resistance here. You have a variable resistance. You change the knob, you turn the knob until there is no more current flowing. If there is no more current, that means there is no voltage drop. For current to flow, you need a voltage drop. It's like water, you need some slope. No slope, no water flowing. Okay, so and then you use the voltage divider and you can find R4. So you do that during it's a typical lab. I don't know if you do it. Maybe it's your lab is not very advanced. You know why? Because it didn't bother making a special lab for you and a special lab for the easy class. It's just the same lab for both. But you should have a lab like this. Anyway, application, but I don't think we use that anymore. That's back then. Okay, so circuit in parallel now. Is that clear for circuit in series? Right, exactly. So if you have a circuit in series, you have a power supply, you have two loads. Okay, then you can even add another load here. You connect everything together. And no one is happy here because not only they're gonna have to share the voltage according to their resistance, but you limit the amount of current because you increase the total resistance. So it doesn't work well in a building. You don't do that, right? So let's see. 60 volt. So first of all, in a circuit in series, the current will be the same everywhere. Everywhere, everywhere, everywhere the same. So if you want to know the current flowing through that circuit, okay, you say everything happens like you have an equivalent load of resistance 6 plus 36 plus 10. So the power supply is 58 divided by equivalent resistance is 6 plus 36 plus 10. and you get about 1.12. Okay, so the equivalent resistance in a circuit in series is always larger than the largest one. It's going to be 36 plus 6 plus 10. As you increase the load, you're going to decrease the current, but you also decrease the voltage. Okay, no one is happy here. Everyone is complaining. Not only the current is less than it would be if it was alone, but the voltage also. Okay, you have voltage drop. So this one will be about 6. Okay, 6. Compare 6 volts here compared to 58. So not happy, complaining a lot. And then this one is a big bully. Okay, because it has a large resistance, it's going to take everything from its friend. Look at that, 40 volt takes everything. Larger the resistance, larger the voltage. And this one is also complaining. This one is also not happy, right? It's going to be about 11 volt. So if you do 6 volt plus 11 plus whatever that was, you get 58 volt. Okay? So instead, we don't do that. We do it circuit in parallel. So in that case, everyone is happy. No one complains because they all get the same voltage. Okay, so they both have the same voltage drop across, and the current that they get depends on their appetite, depends on their resistance. So now they are not complaining anymore. Now so if you have a circuit in parallel, you're gonna drain more current from the power supply. So that's what we use in a house. So if you have 120 volt from the outlet, all the loads will be in parallel. So all the loads will have a voltage drop of 120 volt, and it's not complaining. How much current is going to flow through the load depends on their appetite, depends on the resistance. So they get what they want to get. Okay? If one is not working, like if you turn off the TV, you can still listen to the music, right? So if I go back to here, if this one is not working, maybe this one is fried. Okay, so if I open here, okay, no one gets it. And this one, this one is open, everyone gets it. It doesn't affect the other loads. Okay, exactly. But the issue with this one, especially when you are connected to the outlet, is that because they can drain as much current as they want, according to the resistance, you can start a fire. So that's why here you have circuit breaker. You have fuse, right? Circuit breaker. So if you go over 20 amps, for example, it's going to open the circuit because you are draining too much current. Okay, so let me show you how I do it, the methodology. And well, there is an equation for it, but I'm going to show you how to do it with your TI. So this is called a circuit in parallel. Yeah, yeah. No. Move. Why you don't want to move? Okay, so one way to do it, okay, you have 6 volts, so you have a current flowing here, and then you have I1, so it's like water flowing, and then you have I2, 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 and then I1, and then back to I. So the way I do it is the following. You start with 6 volts. So I show you how to solve, and it will work even if it's not complex. like this. You start with uphill 6 volt, and then I just lost my battery. So you have two branches. Okay, one is 4 ohms, and the other one is 8 ohms. Okay, it's two ways you combine together again, and then you go back to ground. So it's easier to see that. So I, it's like water flowing. So here you're going to have I1, and here you're going to have I2, and then you combine again I. It's like pipes. Okay, you have two pipes, two ways. You're going to have more water here than you have there, because this one is like wider, and this one is tighter, if you think of that. And then I'm going to say everything happens like I'm going to replace this by an equivalent resistance. Okay, so I'm replacing those by one single resistance. It's a mathematical trick. And the current flowing is the current from the power supply, so it's going to be I. So you take your calculator, do it with me, to find the equivalent resistance. Again back. So what you do, you take your TI, so do it with me. So you do 4 to the minus 1. Okay, plus each individual one to the minus 1, plus 8 to the minus 1. You go enter, and then you're gonna enter, you're gonna do to the minus 1 again. So 4 to the minus 1 plus 8 to the minus 1, whatever you find to the minus 1. Boom. That will be 2.7 volt. Not ohms, 2.6666, you see? Now, the equivalent resistance of a circuit in parallel has to be smaller than the smaller one, because it's like having a highway and you add lanes, right? So more lanes you add, less traffic you're gonna get. Okay, so you do it this way. Otherwise, you apply, there is an equation. Okay, the equation is 1 over R1 plus 1 over R2 equals 1 over the equivalent resistance. Okay, so at the end, you have that. Once you have that, then you use Ohm's law. Okay, you say the voltage drop here, it's going to be 6 volts. Okay, it's 6 volts, 6. This is the ground, so it's going to be 6 volts. So you're going to have 6 divided by 2.666666666. That's going to be 2.25. So 2.25 amps, that's going to be the current that you drain from the power supply. Okay, that's the current drain from the power supply. And then you go back one step. So that's going to be 2.25 amps. Some of it will go through here. Some of it will go through there. And at the end, it's coming back. So imagine water flowing. Are you with me? Okay, what's the voltage drop here? Across here, across here. If you're taking a meter, like measuring tape, it's going to be 6 volts. Do you agree? This is 6 volts. It drops. Remember, we are up the mountain and you have two pipes. It goes to the ground. It's going to be 6 volts here, 6 volts there. Agree? Okay, so then you can apply Ohm's law. So 6 volts equals I1 times 4. Okay, so I1 will be 6 divided by 4. That's going to be 1.5. And the other one, 6 volt, will be I2 times 8. So I2 will be 6 divided by 8, 3, 4. Is that right? Which is 0.75 arms. Agree? And it makes sense because you have I1 plus I2 equals I. So this is called Kirchhoff law for currents. It just means, I think Kirchhoff has nothing to do with that, but that's what it's called. You see, at the intersection, whatever comes in has to come out. And that's a nice way to solve circuit in parallel. Yeah. So if you go back to here, all those here, they are complaining, I'm not happy, are you happy? No, I'm not happy. Terrible, terrible situation. So what we do, we say, okay, we heard you. So we're gonna make a circuit in parallel so they stop complaining so much. Okay, so this one is happy. Look at that. The current is flowing really fast. Okay, we're gonna make this one happy. Oh, wow, look at that. Also very happy. So happy that I start a fire because I'm draining too much current. And this one wants to be happy too. So I'm gonna add another branch. No, to the power. I should not do that. No, I did a mistake here. It has to be to the power supply, right? Oh, no, it's good. It's good to the power supply. And this one also wants to be happy. Start a fire. And this one is happy too. So now if you measure the voltage, they're all happy except for the power supply. So this one is 58, so it's happy. This one is also 58, it's happy. This one is also 58, it's happy. So the current will be the current you can find using Ohm's law, right? So 58 divided by 36, 58 divided by 10. Okay, so this is a circuit in parallel. It's a little bit messy, but that way everyone is happy. What do we do, this one or no? Yeah. Find the equivalent resistance between A and C. Okay. I'm gonna help you. I'm gonna show you the engineering way. Okay, I show you. Okay. Try to do. We're gonna do the engineering way. Okay, you start from here. Okay, I start from my power supply. You always start from the power supply. Okay, by power supply. You go for a walk. Boom, 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 boom. Oh, look at that. There's a zigzag here. So I'm gonna make a zigzag here. Agree? And then here you have intersection. So it means you have two pipes, two lanes, right? It's the highway, one lane, you're merging, and now you have two lanes. Okay, you can go this way or you can go that way. If you go that way, you have a R. Or you can go that way, you have another R. Okay, so lane number one, lane number two, boom, 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 boom. Oh, it's merging again. We are merging. Okay, we have to go back to base. So you keep going, boom, 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 boom. Oh, another traffic jam. Here you go to ground. So let's find the equivalent resistance now. See, you start from uphill, la 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 la, traffic jam, boom, 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 boom. And then it goes 2 lanes, merging, another traffic jam, go back to base. Okay, so we go step by step. So omega, this one I'm not going to touch yet. So this one I don't touch. What do you think the equivalent resistance is here? Yeah, so if you want to do 1R plus 1R equals 1 over equivalent, so it's going to be which is what? It's going to be what then? If you have one, let's say you have 1 ohm and 1 ohm, what do you get? What will be the equivalent resistance? 0.5, yeah. Okay, so this one will be R over 2, and then you shift this one, it's going to be R. Okay, you go step by step. You go from here to there, and there to there. Okay, and then what? So you have one zigzag, another zigzag, another zigzag. It's going to be boom, 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 boom. Everything happens. You have a huge one. It's going to be 2 plus 1/2. Yes, 2.5 R. Okay? Have a string. It's 2, huh? Okay. It's already at the same denominator, so it's going to be 1 plus 1 over R. Okay, do you agree? So let me give you a trick. If you have resistance or resistors in parallel and they are the same, you divide by the number of resistors. So if you have R and R, it's going to be R over 2. If you have R, R, and R in parallel, it's going to be R over 3. So if you have, for example, 5 ohms and then another 5 ohms, and they are in parallel, that's going to be 5 over 2 ohms. Okay? We will get back to that, but the answer is 2.5 R. Any question? You go step by step. You start from here, you go there, you go there, you go there, and then you can solve, right? You can say that will be the current here, I. That's going to be the same current here flowing. So here you're going to have a voltage drop V1. Here you're going to have a voltage drop V2. And here you're going to have a voltage drop V3. Think of that as altitude. So that's going to be V1. That's going to be V2. And that's going to be V3. You see, it's like level. It's the same level here and the same level there. You drop V1, you drop V2, you drop V3, you go back to ground. Are you with me? So the current I here current I. Here you're going to have I over 2 because it's the same appetite. I over 2 and back to I. So you have to imagine this is like water flowing in a pipe. The pipe divides in two smaller pipes but the same size, and then they combine again together. Okay. Are we good? 66. Which one is actually equivalent? So you always do the same thing. You start from here, so uphill, and you take a walk. Boom, 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 a resistance, two branches, back together, back to base. What about here? Boom, 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 traffic jam, two branches, go back together, go back to base. A and B. Here, not same. Here you go, boom, boom, boom. I have two branches. In one branch, I have one traffic jam. The other one have two traffic jams, right? So not the same. This one will be in, boom, boom, boom. I have two branches, so two lanes, one traffic jam, and the other one has one and two. And then you go back together. Okay? And then from here, you can say, okay, this branch is R. Here, I have a big zigzag, 2R, and then you go back together. Okay? If you want to find the equivalent resistance, you're going to do something like this, 1 over R plus 1 over 2R, and put at the same denominator. That's 2 plus 1, 3. Okay? Okay, this one I'm skipping. You have to do, you have to, you can think about that. Okay? Okay, let's just have fun. This one 6 volts. So here you are measuring the voltage across that one. What's going to be the voltage across here? 3 volt, very good, right? You start from 6, everyone. So we suppose it's the same resistance, so the same appetite. Okay, so they share. And this one will be 2 volt. This one is in parallel with the power supply. So this one is very happy. It will get 6 volt, very good. This one are complaining because they have to share 3 volt each. So they complain, okay? They have to share the cookies. Those three setup is the same. Okay, it's just different way to draw or connect them, but you see both of them, the three of them, they are across the power supply, so they will get 6 volts, 6 volts, 6 volts, 666, 666, happy, happy, happy. Okay, let's do something in the head just for the fun. You have 60 volts here. So that branch, what's going to be the equivalent resistance? 10. So do you all agree? Keep that in your mind. But this branch here, I have to take care of this one first. 4 and 4 in parallel, that's going to be what? So when the resistance, so that's going to be 2, 2. Okay, so if you have two branches and the resistance is the same, you divide by 2. If you have 3 branches, divide by 3. Otherwise, you do it. So 2. So you have 2 here and 8 here. How much is that? 10. So you have 10 in parallel with 10. So the equivalent resistance will be 5. And then you do 60 divided by 5. Yes, and that will be the current that you drain. Huh? Isn't that cute? It's a nice unit. It's much easier. It's the easiest one. So this is also very cool because this is called the R to R circuit, and it's used to go from analog to digital. Analog to digital. Analog digital. Oh, I forgot how it's called. But oh yes, analog ADC. ADC. Analog to digital converter. So anyway, it's called R to R circuit. So look at that. You start from the end. 1 and 1, it's going to be, they are in series. So it's going to be 1 and 1 in series. It's going to be 2. 2 and 2 in parallel. So it's going to be 1. And then I have 1 and 1 in series. So that's going to be 2. 2 and 2 in parallel. That's going to be 1. 1 and 1 in series. That's going to be 2. 2 and 2 in parallel. It's going to be 1, 1 and 1. 2, 2 and 2. 1, 1 and 1. 2, 2 and 2. 1, 1 and 1. 2, 2 and 2, 1. It's always 1. It's always 1. Okay, so if you're in electronics, you can look up R to R network. And then it depends how many digits do you want, right? It's how many bits do you want? So you go from analog to digital. Okay, so same thing here. You have it's called a complex circuit. So you always start from inside. So this one plus that one, 470. And then from 470 to 180, they are in parallel. Okay, so with your calculator, you will do 180 to the minus 1 plus 470 to the minus 1, enter, to the minus 1, enter. That's going to be 130. And then you have 130, 110 in series. That will be 240. And then you go back, you go back, you go back, you go back. The current will be 24 divided by 240. I brought before I forget, the demo. So this, you remember the plasma globe? I don't know if it's gonna work, but let's try. You see, you can visualize the electric field. You see that? Inside here, you have a Tesla coil. It's very genius because you start with 5 volt and then you go to 1,000 volt. I don't know how much volt, but I'm fine, right? It's not the voltage that kills. And then I can take a fluorescent light and it should be. Can you see that? Isn't that good? So I am at 0 volt because I'm connected to the ground. This is 1,000 volt. And so you apply a voltage. So one, you see, it's highlighting only this part. So there is a tiny current flowing, exciting the electrons of the mercury. Yes, yes. If I move here.
Yeah, I think say the thing that's cutting it off manual motor.
Yes, exactly. I am a shortcut, a live shortcut, right? Isn't that cool? But the current is very small, so I didn't die yet. Okay, so let's do that. Can you find the equivalent resistance?
Yeah, but then you have to do one over that. Do one over this 2.7 class probably. Oh, you're right. Because it's one over. You have to do the one over again. That's just what gives you 1.33%. And we like to do it wrong. Not. I knew that after the distinction.
Okay, so you do this one first. So 2 to the minus 1 plus 4 to the minus 1. Enter, and then to the minus 1. So 1.3 repeating. And it goes big, 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 big. So 3, 4, 5, 5.3 repeating. Okay? Okay, and then the current here, right? So it's going to be 12 divided by 5.3333333. 2.25. Okay, so you go back. So it's like water flowing 2.25. So now you can find the voltage drop. Black here. So it's going to be here you have 2.25 volt. Do you agree? It's a drop, okay? You are up the mountain and you drop. Here it's going to be 2.25 times 1.3333333, about 3 volt. And here it's what is left, right? So it's going to be 3 times 2.25. 6.75 volt. Do you agree? So remember, it's like altitude. Okay, these have the same altitude. So that's going to be 2.25. Here, that's going to be 3 volt. And that's going to be 6.75 volt. For the current, here you're going to have 2.25 amps. That's amps. So here you're going to have I1, I2, and here you have 2.25 amps. Is that clear? You have to imagine a mountain, you go drop and you drop and you drop. Drop, drop, drop. You go down. You flow. It's like a flow. So I1 will be 3 divided by 2. And I2 will be 3 divided by 4. Okay, that's my way to solve. It's copyrighted. There's a copyright. No, if you don't like my way, it's okay. You can do it the book way, the textbook way. This comes from playing with Arduino. So when you look at schematic, they always do something like this. They always this here will be the power supply, and you imagine that you go down and down and down and down up to the ground. Okay, I want to stop soon because I want to help you with a question for the pop quiz. But in your head, 12 volts, 24, 24, 24, they are in series. Oh, sorry, they are in parallel, right? Because it's a highway with 3 lanes. So what will be the equivalent resistance? It's in parallel, you divide by 3. 8, 8, 8. Okay, so the resistance will be the current will be 12 divided by 8. Okay, we finish that next time. I want to help you for this for the pop quiz.
Tap back to the